Okay. Yes. Good evening again, and I welcome you to this fourth doubt session of the Basics of Finite Element Analysis Part 1 course under NPTEL initiative. So, the this is week four. Week four of this course has just passed. So, I'll be covering this basic summary of part of the content, course content, and after that we'll have a brief doubt session, and I'll solve some problems regarding the same content. So till week three, the last thing we studied was the Rayleigh-Ritz method, and after that, in week four, we started with the method of weighted residuals. So I would, can you please answer if what is the basic difference between the Rayleigh-Ritz and weighted residuals method? You can type in the chat box or unmute yourself and answer.
Sorry, sir, I'm not sure how to word it.
Okay. Do you remember anything about Rayleigh-Ritz method? What was the procedure for that? You can answer whatever you know. It's fine. Okay, I'll repeat the question. We're starting with the method of weighted residuals this week, and I am just asking how was the Rayleigh-Ritz method different from this method? Can you just point out one or two differences? You can type in the chat box, or you can just unmute yourself and answer. Is my question clear, by the way? Okay, so since so many have joined just now, I'll repeat whatever I just said. Okay, so the, okay, yes, that's what exactly what I asked. So I'll repeat for the others. So we are starting with the method of weighted residuals this week, and last week the last thing we studied was the Rayleigh-Ritz method. So can someone point out the basic difference between the two methods? And why exactly are we studying weighted residual method since all we've already studied rates, right? Why do we need weighted residuals? Yeah, right, Kumar. So in weighted residuals, we do not need to write the weak form. Yeah, differentiability is not weakened here. So, can someone tell me why we need weighted residual method? What is the shortcoming of the Rayleigh-Ritz method? Why do we need to study other methods? More flexibility in choosing weight function. Uh, but what effect does it have on our solution, right? We, if, if we are allowed to choose, say, limited number of weight function, Does it really affect our solution because of differentiability? I'm not sure about this. Uh, One thing that was clearly told in the lecture was that the Rayleigh method does not work when the function becomes non the differential equation becomes non-linear. So that is one great limitation of the Rayleigh method. So, anyways, we have other method. We will study them. So we start with the weighted residual method. Here, the fundamental difference, as told by Kumar, is that the differentiability is not weakened, unlike the related method. So, of course, we won't easily expect the bilinear form to be symmetric and thus the metrics coming out to be symmetric. It's not. It won't be naturally. It might be in some cases, but naturally it won't. We can't expect. And the second consequence that comes into action is that since we are not taking the weak form, so we don't have the boundary term in the equation. It's coming on its own, like we used to have in the weak form. So the natural boundary condition used to be satisfied with that term, but since we don't have that term now, so while choosing the weight function we have to ensure that the weight function satisfy both natural boundary condition and the essential boundary condition. And of course, yeah, we don't need to choose the same weight function since there is no matter of symmetry here by default. So it's not required. We can choose any function that require that fulfill certain criteria, of course. So how we proceed is we take an approximation of the solution by choosing certain weight function. So uh, this is an unknown constant, unknown, and these are known functions. We choose them based on the boundary conditions. So this function must satisfy the boundary condition directly, and this function must satisfy the homogeneous form of a boundary condition. And by substituting this function into the our differential equation, we find the residual. So basically, if we have some differential equation, Cx equals to Gx. So residual is basically everything towards basically left hand side minus right hand side. So we have. Uh, can anyone tell me why do we call this as residual? Yes, homogeneous means when right hand side is zero. So when you say homogeneous boundary condition, so suppose boundary conditions are defined at u is equal to 5. So the homogeneous form of this would be u is 0 equals to 0. So we turn the right side to 0. Can anyone tell me this was supposed to be 0, right? If we uh, take right hand side minus left side, this is supposed to go to 0. Yeah. Why do we assign it as uh, r residual when we are substituting the value of un here? Can someone tell me this? Please feel free to unmute yourself and answer, or you can type in the chat box. Right, right. Okay, we're taking elements. Not exactly elements, but we are basically taking the approximation for you. So if this is our differential equation here. So when substituting some value for, if we know the exact solution for you, we'll substitute the exact solution here, then of course we should get 0. But we don't know the exact solution, right? And we are substituting an approximation. So so whatever this would come, this would definitely not be equal to 0. So we assign it some value, we say call it to be residual. That is error basically. So uh, and we minimize that error by our weighted residual statement. That's what we studied in our earlier classes. So we get the residual here, and and then we get the weighted integral statement. So we multiplied by residual by each weight function and integrated over the domain and equate it to 0. So in order to minimize our residual. So again, the weight function must satisfy the same conditions as before, uh, except now the weight function must also satisfy the essential boundary condition. No, natural boundary condition as well. Earlier it was only essential boundary condition. Apart from that, all the things are same. The function should be linearly independent and it should form a complete set. And of course, they should be sufficiently differentiable as well. If things would blow up to be 0, then we won't get any equation. So, what are the different types of weighted residual methods? So, the first one is the Petrov-Galerkin method, where the weight functions can be any function different from the approximation function chosen for the variable u. And then we have Galerkin method, where the weight functions are essentially equal to the approximation function chosen for u. This method is also known as Bobnov-Galerkin method, if I remember correctly. It's Bobnov. It's called Bobnov-Galerkin. Of course, here metrics will never be symmetric, and we'll give same answer as the Rayleigh-Ritz method, since we in Rayleigh-Ritz method also we used to choose the same type of functions. Although we won't transfer differentiability here, just like in Rayleigh-Ritz method, but the solution would still remain same. The answer would still remain the same. There's nothing big difference in there. And then we have the method of least squares. So now what we want to do is minimize this quantity. This is the integral of square of residue. And in order to minimize this, so R is basically a function of CJs. So in order to minimize this, we need to take the derivative with respect to CJs and equal to 0. So therefore, the weight function in this case is this dou R by dou Ci. And the last one we have the collocation method, where the weight function is the direct delta function, and we multiplying the residual statement with this function basically gives us this statement. This would be our final equation what we get. So we have four different type of methods. The only difference among them is the way we choose our weight functions. That's it. So we'll solve some problem based on this later. Next, we started with the finite element analysis formulation. Okay, so there's certain things that we need to understand before starting FEM. Uh, can someone tell me how is the finite element method different from any other method we studied so far? Even okay, yeah, you guys can tell. The method we studied so far, all the weighted residual methods and the related method. How is FEA different from all these methods? Trial functions. Okay. Trial function is it's basically other name of the the approximating the solution, the function we chose. So that's the same thing. We choose some approximation function in the other methods also, and we do the same in FEA also. What other difference can you think of? Someone else would like to answer? Come on, think of it. There's very fundamental difference between FE and other methods. Anyone would like to guess? Question. Okay. Uh, I didn't get your point actually. I was just I was asking what is the difference between finite element analysis, finite element method, or uh, with between the what is the difference between finite element method and the other approximation method we studied so far, like the Rayleigh rates and the weighted residue, or in simply how is FEA different from the other methods? Are not all weighted residual method. Yeah, but they have something different in the way we start with. Of course, we start with the weighted integral residual statement. Yes, U1, U2 is value of okay values of yeah at nodes value of solution is nodes, right? But you have jumped ahead. You need to answer the basic thing before that. That is right. U1, U2, U3 are the solution at the nodes, but what main difference come before that? Anyone want to try, or should I tell? Okay, so I'll tell you. So we have say u is our solution, is a function of x, and we have some. This is our solution, actual solution. So what we do is uh, in other methods, what we do is we take some random polynomial and try to approximate this thing with with that thing, some random polynomial. We call it an approximation of UN. But what in FEM what we do is we discretize. The fundamental difference between FEM and others is discretization. So suppose say this UN what we approximated might be some 3-4 degree polynomial. But in FEM, if even if we take a linear approximation, you see our solution is much closer to, while approximating our approximate solution is much closer to the exact solution in comparison to the other methods. So discretization gives us a major advantage uh, in the closeness of the solution, and secondly we don't have to use higher order polynomial functions. So this reduces our calculations also. So this way of plus there's another important advantage is that our in reality our domain can be a very complicated surface or shape uh, for which solving these weighted integral statements and solving those integrals would be in 2D and 3D it would be a very difficult job. But in FEM, what we do is we discretize, say, if it's some random shape, we discretize it in form of triangles. So for these things, we know the approximation solutions, and these integrals are much easier to solve because we have formulated our integral statements and functions in such a way. So this is much easier to solve for these compared to the any random shape of domain. So this is the advantage of discretization. That is why we are we are studying FEM, and this is why it is much more powerful than the other methods. Okay, so we'll start with the FEA formulation. So of course, the first step in FEM comes as the discretization of the domain. So first we discretize the domain, and we get the weak form. So basically, what we do is uh, we discretize the domain, and for each element, even we are so our whatever a weighted integral statement is, sorry, whatever a weak form is, it would hold for entire domain, right? So it would hold for each element individually also. So we write the so basically if we take it for one element, so our integral would be only for that element over that element, right? Whatever would be coming from this weak form. So we write the weak form for each element, and then the next task is to develop the approximation function. Yes, yes, exactly. From here we started working. So even for solving in the individual element, the method we use is similar to what we have been doing in weighted residual and all these things. But the major difference come in discretization of the domain. So you see, we are solving the same, we're doing the same thing, but on elemental level. And then we will have multiple equations. We'll combine all those for the domain. We'll see, and we'll do things further. So we the next thing is we develop the shape functions for each element, the approximation functions. And in class we have seen how we do it for linear function. And there's another thing is that we define a separate coordinate system for each element. Like we have a global coordinate system that is applicable for the if we think on a large scale we see all elements we so we have This is our domain. So this is 0 x equals to 1 x equals to like so it is x equals to 5 maybe. So this is defined on a global scale, all the coordinate in an absolute sense, you can say. But there's another scale, another coordinate system, another scale we are concerned is the elemental coordinate system or the local coordinate system. So here we just pick out one element and we define the things for that. So we take another variable x equals 0 here, x equals to say element length. So basically, if we'll do this, if we'll define a local coordinate system for each element, so you'll see we'll have, if we take this element also, we'll have same type of coordinate system for, okay. So the equation that would come up would look exactly similar. Of course, we can later do the transformation and transform the. There are some certain ways with which we can transform the local coordinate system to the global system. That final transformation can be done when combining all these equations. But on individual level, this thing can be just for each element. This same process can be repeated for each one. Okay, so this is the way we transform the each variable from a local to global sense. And similarly we get different type of in terms of local coordinate system we get the respective interpolation functions. Okay, and this interpolation function which we got in the class was the Lagrange family of interpolation function. So this is basically derived by just using the value of the directly the value of function, but there's another set of family of shape functions which also considers the derivative of the of the primary variable. So that is called the arithmetic functions. So these type of functions would be used in the in beam problem, where the slope of the beam is also required as a main variable. So that we'll discuss later. Uh, and one thing we'll see about this shape function is that they satisfy this property number one. So they should give a value of 1 at whenever at the respective coordinate. So if we have node 1 here and node 2 here, so the shape function 1 at x1 would give 1 and shape function 1 at x2 would give 0. So in order, so we'll have a value of this psi 1 as this. And similarly for psi 2 we'll have this. So at the if we take the solution here as u1 psi 1 psi 2. So at x1 we'll automatically get the value as u1. And the other thing is that if we take the summation of these shape functions, we'll see if you add these two functions, you just add these two, you'll see you'll get 1. Okay. So this is also one of the properties. There are other properties, maybe we'll discuss in the later classes. So yeah, that's what we did in this week's session. Uh, you're welcome to ask if there's any doubt. Otherwise, I'll move forward with the discussing some problems. Question, let me check. So okay. In class, sir told that number of nodes in global is n plus 1, but for local it is 2n. Uh, well, let me see. So if we have So if we have say five elements here, so we'll have six nodes, right? I don't think sir said two, and it must be two, or let me check. So can you tell me what does n stands for here? Do you remember? Number of elements. Mm, But for a local system, n doesn't make any sense, right? N is basically there's only one element we are worried about, right? In local. N might be the number of nodes or the number of interpolation points. That would make sense. So suppose we take linear elements only, right? We have five elements here, so we have say five elements, so we have five plus one, six nodes are there. And if you take consider one element, we have only two nodes. Suppose if we want three noded element, we'll take only two elements. We want three noded elements. See, for linear, you will only have two nodes for an element and number of elements plus one nodes for global. I think you are mistaken. It must not be two and it must be two for linear case, right? Because for case of linear, if we take one element, we'll only have these two nodes here. These two only, two nodes. Uh, Suppose if we go for quad, uh, quadratic elements, for two elements we have uh, it's 2 and plus 1, I think, 5 nodes. Yes, 5 nodes. And for each element we have 3 nodes. Yes, the odd n plus 1 nodes. The n is basically the order actually, order of the polynomial. I think it must be that only. Okay, is there any other doubt? Okay, then I'll move forward. Thank you. Okay, so we are giving a differential equation here. This is a differential equation given here, and we have given certain boundary conditions. So we need to write the weighted residual statement. Okay. So what is the first step we do? Please answer. Please guide me while I solve this. What should be the first thing I should do? Please, okay. As integral formulation. But to get residual, integral formation is the thing we do after getting a residual, isn't it? You mean to say this one, right? Weight function times residual. You mean to say this, right? Is this what you were saying? Anyways, can someone else tell me how should I proceed? Please, I want this to be a sort of discussion, so it shouldn't be monotonous. Otherwise, it gets really boring for you also, and for me also.
That same differential equation is the residual means d square e by h square minus u.
Uh, we are dealing with the residual statement, right? The residual method of residual. So we don't need to get the weak form and all, right?
Yes, sir. Yes,
So
sir.
residual statement is right now just this. Okay, actually an approximation. So the UN is the approximation of you. So what do we do from here? Someone I think typed in the chat box. Not a residual, but is not a residual the differential we view. Residual is not the okay differential. What do you mean by differential? Isn't this the residual, right? Right, right. We should search an approximation. Not for the weighted integral, we should search the approximation for this. So we approximate this as I to n ci phi x. Okay, so this is what we are going to think of. Like we'll choose some function for these. So how should I choose this? Firstly, we'll choose phi naught. What should be the requirement to choose phi naught? The first basic requirement. Boundary condition. It should satisfy the boundary condition. Exactly. So phi naught should be a function that should be uh, for x equals to 0, it should be 0, number one. And since it's a weighted residual method, so we need to satisfy the natural boundary condition also. So if I take its derivative, so for x equals to 1, it should be 5. What if I take this as 5x? Would work, right? So if we take substitute x as 0, we'll get 0. That's this first one is satisfied. And if we take its derivative, we'll get 5. So for any x, we'll get 5. This is also satisfied. Okay, fine. And for how should so we'll choose one or two functions here. How should I choose phi one? Yes, exactly. It should satisfy the homogeneous boundary condition. So, of course, again, the first boundary condition is homogeneous. Yeah, you gave an idea, right? X into x minus 1. I try if this works. Okay. So, for first is, of course, this is the already a homogeneous in homogeneous form. So, this is being satisfied, right? For if we'll take x equals 0, it will go 0. If I take its derivative, so it would be 2x minus 1. And for x equals to 1, this would be 2 minus 1. Won't be 0. Okay, this won't work. No, no worries. At least you tried. But okay, we'll see from here how could I have got it at 0. So if I would have had this term as 2, this would work, right? So what if I put x minus 2? Someone answered this here? I'll check. Okay. If we put it as x into x minus 2, so the first condition is already satisfied, right? This won't go away. And for second, we'll have 2x minus 2 as the derivative, and if we put x equals to 1, this would work. Okay, and right. So can we think of some other function p2? So this is actually x square minus 2x. What if we just multiply this by x cube? No, this won't work. Second one satisfied. If I just put it as 3x square minus 2x cube, or just the opposite. So at x equals to 0, it would give 0, of course, and its derivative would be 6x minus 6x square. So if I put x equals to 1, I'll get 0, right? So this is satisfying. Good, okay, nice. So was this clear how we chose these functions? Again, for our residual statement, what we'll do is we substitute these. So u is now c1 p1 plus c2 p2 plus p0 minus u. So c1 p1 minus 2p2 minus p0. Choose with trial, but maybe others. You choose with trial, but can I couldn't understand your question. Sorry. Can you repeat? Can you reformulate the question? Do you mean to say that the way we chose this function was just trial and error method to satisfy boundary conditions. I'm sorry, I couldn't understand your question. To satisfy the essential boundary condition. Sorry, I still couldn't get your question. Can you reformulate it in one statement? It's fine, you can take time to right. I'll proceed with the solution. So we have okay, can you choose sine cos function? Of course we can. There's no limitation of choosing sine cos function. But dealing with those function differentiating and thus some later stage we want to integrate also. So the product of sine cos function integrate that is not a very pretty thing to do. So we'll be in trouble later. So that's why we work with polynomials only. It's much easier. Okay, thanks. Okay, then we have c2 by d square by d2 by okay. So what is the second derivative of phi1? So derivative of phi1 is 2x minus 2. So we'll have 2. 2 only. And for phi2, 6x minus 6x cubed. 6x squared. So taking derivative of this, we'll get 6 minus 12x, isn't it? Yeah. And for phi naught, it would be 0. It's 5 for first derivative and 0 for second. Okay, so what would our residual be? 2c1 plus 6 minus 12x c2 plus 0 minus what is p1 x square minus 2x c1 minus 3x square minus 2x cube c2 minus 5x. Combining all the coefficient of c2, we'll get c1 and c2. 2 plus 2x minus x square times c1 plus 100 plus c2 6 minus 12x minus 3x square plus 2x cube times c2 plus minus 5x. So this would be a residue. Okay. Is that fine? Is there any doubt? Or I'll move forward. Let me know if there's any doubt. Okay, for finite element ranging between x a equals to 0.2 to x b equals to 0.5, find the linear approximation function. So in the class we have derived the formula for the linear approximation function, isn't it? So we since we are given in terms of global, we talk in terms of global only. So x equals to 0.2 here, x b equals to 0.5 here. So basically, shape function should be 1 at each node plus psi 1 psi 2. So what was the formula? I think psi 1 was x minus x b upon he, right? Or instead of he, right, x b minus x. Let me just check the formula. Hold me a number. X b minus x upon x b minus x. Sorry. I wrote opposite. So what is x b? 0.5 minus x upon 0.5 minus 0.2. What we get here is 0.5 minus x upon 0.3. We can get 5 minus 10x by 3 for simplicity. And for side 2 we have x minus x a upon xp minus x. So we have x minus xa is 0.2 and 5 minus 0.2. Okay, so this would be a shape function. So you see, one thing you'll see that for different elements. So say this was 0.2 to 0.5. If I take say 0.8 here, if I take for this element, we'll get some different shape function. The value because they are directly dependent on x and xp in because they were in global system. If we would have worked in local system, all shape function would look similar for each element. Okay. Okay. So for the bilinear form given the equation of the problem one, find the simple matrix in terms of element coordinate system. Okay. Okay, we'll do that. What was the bilinear form in problem one? Okay, so we have this. First, we need to find the. Sorry. So to get the bilinear form, what we need to do is find the weak form. So what binary term we'll get from here? I'll just directly write it. If there's any doubt, let me know. Sorry, it's a B plus. Okay, this is the binding form for this. So what we have to do is first get the shape functions. So for local coordinate system. Okay, 1 minus x per by h, right? X per by h, x by h, and side 2 is x by h. Okay, so we get 1 minus x, and here we get x. Simple. So, and so we basically consider the integral from 0 to 1 for since basically it's 0 from 0 x bar x is from 0 to h e, h is 1 of course. So this for our given element here, this is our domain. So for bilinear form, our integral would be from 0 to 1 du by dx du by dx. Okay, so when we write the matrix, separate matrix, we'll just replace it by the shape functions. Okay. Psi. Okay. So this is how we'll get the stiffness matrix for this element. So what would be K11? Derivative of psi 1 would be, okay, so let's write the psi 1. Both would be 1, right? This would give psi 1 would be minus 1. Sorry, psi 1 is 1 minus x, so its derivative would be minus 1. And we have 1 minus x square. So, okay, so we can just integrate this thing and get some answer. So I'll just quickly go through others also. And for K12 we'll have 2 psi 1 by dou x, 2 psi 2 by dou x, psi 1 psi 2. And since you know this is symmetric, so this will be equal to K21. You can similarly put the value of psi 1 psi 2 and the derivative and get the similar answer. And same for K22. We have this 2 psi 2 by dou x, 2 psi 2 by dou x, psi 2 psi 2. You can just indicate this simply and get the post-treatment matrix each term. K11, K12, K21. Okay, so this is so simple for just one single element for linear shape functions. All right. So I think we are about almost out of time. So if there's any doubt, I can address them now. Otherwise, we can just end the session. How to choose weight function here. So Kumar, for FEM, the procedure of choosing shape function is very pretty straightforward, and there's a defined method for this. So for linear functions, we have derived it earlier. Okay, so we are just straight away going to use that. So our shape functions must be in such a way that it satisfied that condition. Let's write it here. So we Up. There's no space. I'll write somewhere else. Okay, we have some space here. Right here. Okay, so we choose UN in such a way that UN psi 1 plus u2. So suppose we take only two functions for linear case. So what should be the condition that at first node of at UN at x1 it should give me u1, right? And UN at x2 it should give me u2. Okay, so at first node our value should be equal to the exact the value of u1. So this is the way we choose the shape function, derive it in that way. So every time, be it any problem, any case, you're going to use the same shape function if it's for the case of linear 1D elements. So every time it would be the same shape function. For different type of element we'll derive the different shape functions. So that is one advantage of FEM. You don't need to uh, put in trial and error and waste time in choosing the shape function. There's a predefined method to choose the shape function, and we just go with them every time. That's why it is so convenient to write solver codes for FEM problems. Okay. What is the question? Psi I you can use weight. I couldn't get your question. Psi I we can use it weight. Psi
For
I.
the weight function, this psi1, psi2, we can use as weight function.
Yeah, exactly. They're actually weight functions. So they're both approximation function and weight function here. So where if you'll see, observe, we're using the what we did in the relay rates method. We're doing exactly the same. We're lowering the differentiability, and we are choosing the same function for weight function as we did for the approximation function. So that's why I earlier told you that the way we solve it is not different in FEM. We all what we did in it's all is done, but now it's in on specific domain, specific elements. We define these things. So that's why our approximation function come out to be same every time. Okay. Yeah. Yeah. Thanks. So if there's any more question, I can address it now, or we can end the session. Please let me know if there's no questions. All right, then I'll conclude this session. Thank you so much for your patience, and we will meet in hopefully meet in the next session. Thank you all. Thank you all for your participation.